Hello people, Zach here again today, and today's video is going to be a math video on Quaternions. And the subject mainly came up to me because Alexander Unzicker recently posted a video talking about the subject of Quaternions and their relation to the fundamental physics. And he's brought them up numerous times in the past, and there's just a part of it that what he says is kind of gets under my skin a little bit. And just to preface this with this video, I'm not saying that I'm the most intelligent person on the face of the earth. I'm far from it. There's certain things that I can mathematically prove and show, and I want to get into this. So the definition for quaternion components, I guess you should say, I squared is equal to j squared is equal to k squared, which is equal to ijk, which is equal to -1. Now, there's actually two different types of definitions that are packed in here. The I squared is equal to j squared is equal to k squared equals -1, and the ijk is equal to -1. And the second part is defining how these particular components commute with each other. So ij is equal to k, jk is equal to I, ki is equal to j. Now, my argument for this particular video is that actually that second definition is wrong. It's not supposed to be -1, it's supposed to be +1. And the rules that fall out from that is that ij is equal to -k, jk is equal to -I, and ki is equal to -j. And the reason for this actually has to do with geometric algebra, or Clifford algebras, I guess, if you want to call them that. And so the basic idea behind it, if you look at something that's called the geometric product, or also called a rotor, is that if you take two vectors and you multiply them together, the sum of the two vectors is the sum of the inner product. The product of the two vectors is the sum of the inner product and the outer product. And the inner product is, of course, the dot product, which is the magnitude of the first vector multiplied by the magnitude of the second vector multiplied by the cosine of the angle between them. And this is a commutative operation, so u dot v is equal to v dot u. Now, the outer product is also known as the wedge product, and this is actually a bivector, but the magnitude of this bivector is equal to the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. And so unlike the dot product, the outer product is actually anti-commutative. So u wedge v is equal to -v wedge u. And one of the consequences of this is that if you wedge a vector with itself, so like u wedge u should be equal to -u wedge u, which isn't really possible unless u wedge u is equal to 0. And this actually just extrapolates to the general set of things, which is that because the sine of an angle that is 0 or 180 degrees is always 0, anytime that you have two vectors that are hang on, I said that right. I said that because the sine of the angle that is 0 or 180 degrees is always 0, what it means is that anytime you have two vectors that are parallel to each other, the wedge product is going to be equal to 0, and so the geometric product, which is uv, just simplifies to the inner product, which is u dot v, which is commutative. So anytime you have two vectors that are parallel, the geometric product becomes commutative. But inversely, because the cosine of an angle that's 90 degrees or 270 degrees is equal to 0, anytime that you have two vectors that are perfectly perpendicular to each other, the inner product simplifies to 0, which means that the full geometric product, uv, becomes equal to the outer product, and thus the geometric product becomes anti-commutative, which means that uv is equal to -vu. Now, because of the way the rules of these things work, if you take one of the vectors and you square it with itself, the wedge product cancels out, and you're left with the dot product of the vector with itself, which is, of course, equal to the square of the magnitude of the vector. But when you go into talking about the it's just going to go into talking about the outer product a bit more. So, in the 3D space, we have 3 different basis vectors. We normally call them the x-axis, the y-axis, and the z-axis. And these are usually represented by unit length bivectors. And if we take the dot product, we can sort of project any vector onto these 3 basis vectors. We can do the same thing with bivectors. A bivector is sort of like a plane. It's the combination of 2 vectors, but it's oriented. So like if you do u wedge v, it goes like that. But if you do v wedge u, it does like that. So like one will give you one rotation going that way, and the other one will give you a rotation going that way. But just like with vectors, how you can take any vector and project it onto the basis vector plane axes. With bivectors, you can take any bivector and project it onto the basis bivector planes, which are formed by the basis vectors. Now, given the rules that we've talked about before, we know that if we take any of these basis vectors and we multiply it with itself, because it's always parallel to itself, the outer product cancels out, and you're just left with the inner product, which is equal to the square of the magnitude of that axis. And because it's a basis vector, which is unit length, it just becomes 1. So basis vector multiplied by itself is just equal to 1. But if we take the 2 different unit vectors and we try to multiply them together, well, by definition, the 2 basis vectors and try to multiply them together, by definition of the basis vector, they're always perpendicular, which means that the dot product part cancels out of the equation and it becomes anti-commutative, and also equal to the wedge product, which is the outer product. But of course what this means is that the x-axis multiplied by the y-axis is actually equal to negative of the y-axis multiplied by the x-axis. Now, this is a little bit long-winded to try to get to the meat and potatoes of this entire situation, which is that if you take any of these 2 basis vectors and you multiply them together, of course you get the basis vector plane. And that's actually, these bivectors that result from these operations, they are the I, J, and K components of a quaternion. So, like your XY plane is, we normally label these things as E with the subscripts, like E sub 0 would be the x-axis, E sub 1 be the y-axis, and E sub 2 would be the z-axis. But like I said, these are all bivectors, and the I, J, and K components are equal to each of these basis planes. So I think is the E sub 0 times E sub 1, J is equal to E sub 1 times E sub 2, and K is equal to E sub 2 times E sub 0. So I is equal to XY, J is equal to YZ, and K is equal to ZX. Now, if you take any of these individual planes and you square them, you actually reach the result that they're equal to -1. So the first part of Hamilton's definition, that I squared is equal to J squared is equal to K squared is equal to -1, is correct. That comes out correctly. But when we get to the second part, if you try to multiply 2 of these things together, so IJ would be equal to E sub 0 times E sub 1 times E sub 1 times E sub 2. And you notice that there's 2 E sub 1s in there that are right next to each other. Those will actually cancel each other out just to become 1, because they're simplified to the dot product because it's parallel to itself, of course, and the magnitude of the vector is 1. So now you're just left with E sub 0 times E sub 2. And because we know that this is anti-commutative, it's actually equal to a negative E sub 2 E sub 0, which is equal to negative K. So, like when you work out the math, what you see is that it's actually IJ is not equal to K, it's IJ is equal to negative K. And the same rules actually fall out if you do the other multiplications for the other basis planes. And the end result is that IJK is actually equal to 1. Now, this is a mathematically proven thing, by the way. You don't have to... This is not an opinion. This is not a subjective thing. This is not a convention. This is a mathematical fact. Like, you can prove it on paper. And unlike quaternions, which only work in 3 dimensions, And of course, they go up to like octonions or something like that. There's another step above that. But unlike quaternions, because we've tied this all the way down to the sum of the inner and outer products, we can extrapolate this to an infinite number of dimensions. So it seems to me that the objectively correct definition is the geometric algebra approach to this thing. And that Hamilton, his part of his definition, the ijk is equal to -1 part, was wrong. Now, we would ask the question, why is it that when we use quaternions, we can still get the same result? And I believe it's the case that because a quaternion is equivalent to a rotor, which is just the product of two vectors, and because it's multiplied on both sides, that you're still getting to the same destination when you rotate a vector. It's just you're going like the opposite way around. But other than that, the result, I think, is mostly the same. But both quaternions and rotors, they're the sum of a scalar, that's a real part, and a bivector, that's an imaginary part. But just quaternions, they're erroneously, the imaginary part is interpreted as a vector, but it's actually a bivector. And just like how a vector, you can represent it with three components, the x component, y component, and z component, a bivector, you can represent it in three components as the xy component, the yz component, and the zx component. So, but of course you would have to multiply those by like some term that says this is not a scalar, don't combine it with other scalars, and that would be your ij and k. Or alternatively, if you want to, your e sub 0, e sub 1, your e sub 1, e sub 2, and your e sub 2, e sub 0. But yeah, I just wanted to point this out because he's focused on quaternions, or Alexander Unzicker in particular is focused on quaternions, but I don't think he realizes that half of the definition of quaternions is wrong, and that the better place to be looking would actually be geometric algebra. But anyways, this is probably a boring video for most people, but thanks for watching.